In this video, we're going to focus on another geometry problem with limits, and it's another surprising problem similar to the two-circle problem where we expect the limit to be something vanishing or infinity. In this case, again, our limit will actually be finite. So let's just look at the problem and get into it. In this diagram here, you can see a parabola, and the parabola is just y equals x squared. So this is the simple parabola centered at the origin, where for every x, the y value is just x squared. Now we look along this parabola at various points, and specifically now we're looking at this point here, P. Maybe I'll write that out a little bit larger. And this point P can be connected with a straight line to what we call the origin, or the point where x and y both equal 0. So right there. So that line, the connecting line, is this blue line here. So we're connecting the point P to the origin with the blue line. Now, this line now can be analyzed, and we can take a perpendicular bisector of this line, and we'll find that it intersects the y-axis at the point L. So right here we have the point S, which is where the line bisects the OP line, and it connects to the y-axis at the point L. So we have another line perpendicular to our first line that intersects the y-axis at the point L. And the question is, what happens to L as P approaches the origin along the parabola? So we can take P and make it approach the origin by taking smaller and smaller x's. As x goes to 0, so does y, which is equal to x squared. And the question is, what happens to L? How does L change? And does it have a limiting position as P gets closer and closer to the origin? As I hinted before, we will be surprised to find what that limiting position is of L. Okay, so this is a presentation of the actual problem. How do we solve this? Well, again, we're looking for L, right? And in order to find L, what we really need to know is the formula for the line that connects L and S, right? The line LS. So we need a formula like y equals a times x plus b that defines this line LS. So we have to find the slope of this line and the constant value b. And by finding that, we will figure out what L is. Really, all we need is b, but we will not be able to find b without first knowing a. So how do we find the slope and the constant? Well, we know a few things about this line LS. What do we know? Well, we know that the slope, right, of LS is as a perpendicular line to OP, the slope is perpendicular to the slope of OP, right? What does that mean? That means that if we know the slope of OP, we can figure out the slope of LS. What else do we know? We also know, so that's one thing we know. The second thing we know is that LS bisects, or intersects, really, intersects OP at S, which is the midpoint, right, of this line. So if we can figure out what the coordinates of S are, and we can figure out the slope of LS, then we will have this equation here for the line, and we can figure out how L behaves. Okay, so let's start with the slope. So how do we get the slope? Well, let's look at OP. OP. What we know about OP is that it goes from the coordinate 0, 0 to the coordinate, what is the coordinate here? Well, we have x equals p, and that means that y is just p squared, right? Because that is the formula for this parabola. Y equals x squared. Okay, so if we know these 2 points on OP, we can find the slope. Remember, the slope is just the difference in y divided by the difference in x. So what do we have here? The slope is just p squared minus 0, right? That's the y on the parabola minus the y at the origin, divided by our x on the parabola minus the x on the origin, which is just 0 again. And so we have p squared over p. So our slope is just p. So this is the slope for OP, right? Okay. Now, if we know the slope on OP, we can figure out what the perpendicular slope is. What is a perpendicular slope? The perpendicular slope from geometry is just negative 1 over the inverse of the slope. So it's minus 1 over our OP slope, which is just p. So again, it's negative because it's going in the other direction, right? It's going down rather than up, and it has the inverse size because it is perpendicular here. So our slope, our A here, as we wrote it out here, let's maybe use a different color. Our A now is equal to negative 1 over p, where again, p is just our point here. Okay, so we have our first piece of information. Now, we would like to know what the constant term here is, right? How do we get that? We get that from looking at the coordinates of S. So we look at this point here. Okay, so how do we figure out the coordinates for S? Well, the coordinates of a midpoint of a straight line are basically the average coordinates of the 2 points. If we look here on this curve at the value of this angle alpha, we can determine it by using the lengths in this graph. How do we do that? Well, if we look at it carefully, let's, for instance, start with the cosine. So cosine of alpha equals the, let's write the x of s, so the value, the x coordinate of s, divided by this length here. This length here is just half of the overall length of OP, right? Because it's the bisector. On the other hand, cosine alpha also equals the, the half here. Cosine alpha also equals the x value of the point P, which is just P, right? Divided by the total length, which is OP, right? Now, if we compare these two, then we get XS equals P times half OP divided by OP. So the total is that XS equals half P. So we know that. Now how do we find Y? In a similar way, but in Y we just look at the sine of alpha. So sine of alpha equals, again, now we have the height of at S, so we'll call that YS, divide by half of the length OP. And on the other hand, sine alpha equals the Y at the point P, which is just P squared, right? Because it's on the parabola, divided by the entire length, which is OP. Again, if we compare these two, we find that YS equals half of P squared. Okay, so now we have for the point S, we can say that it's at half P and half P squared. Okay, So we have the coordinates at S, and we have the slope. Okay, so now how do we find our line? We have our A. Our A is just negative 1 over P, right? We found that earlier, right here. And we have a point on the line, this point S. So let's write this out as the formula for a line. And we have to figure out what our B is. How do we do that? Let's substitute, right, from this point into this formula. So what do we get? For our y, we have just half p squared equals negative 1 over p, that's our slope, times the value of x at this point A, s, which is just half p, plus b, right? Okay, now this p and this p cancel, and what we get is half p squared. Let's move this over to the other side. Plus half equals b. Great. Okay, so now we can go back to our line and just write it out as y equals, again, our slope is minus 1 over px, plus half p squared plus half. Okay, so this is our formula for the line LS, right? That was our original, from our original picture, this line right here. Okay, so now we just have to figure out what point does this line cross the y-axis. Well, it crosses the y-axis when x equals 0, right? Right there. And we want to find the value of L or Y at that point. Well, when x equals 0, we just have y equals minus 1 over p times 0 plus half p squared plus half. Okay, and we're going to call this actually L. So our L is just half p squared plus half. Now, our original question was what happens when p, right, goes to 0, when our point on the parabola goes to the origin. What happens then? Okay, let's write that out formally. Then we have the limit L when p goes to 0 equals the limit when p goes to 0 of half p squared plus half, which is just half. So our intuition would have said probably that as we go closer and closer, the midpoint gets closer to 0. This point will go to 0 too. But what happens is that the angle gets bigger and bigger as we go to 0, right? The angle is given by the slope, which is just 1 over p, right? Negative 1 over p. And as p goes to 0, this number, 1 over p, explodes, right? The limit for that is at infinity. And so what we find is that as this becomes very, very big, but as the point p and p squared go to 0, 0, the combination of those two leads to a limit that is finite. And that is kind of surprising, and we wouldn't have realized that by just looking at our initial diagram of the problem here. So this was a very detailed solution for this geometric limit problem, and I hope it was helpful. This again is another problem that can be often found in calculus exams and homework, so hopefully this was helpful. Thanks for joining me again, and I'll see you next time.